Welcome everyone to Jackson presentation. And then Ivana, I'm Alejandro Russo, I'm faculty here, and I'm the examiner of both of them. So I know that maybe some of you students need my signature after the presentation, so don't let me go without signing your papers. All right?
Okay, thank you guys. My name is Jackson Isaac, and I'm a student from the University of Gothenburg. I'm doing Masters in Computer Science. I'm here to present my thesis work, which is titled The Performance of Tls Protocol in Vehicular Embedded Computers. So throughout my presentation, I'm going to start by giving a brief background of the project. I'll talk of the goals of the thesis work and then methodologies that I used to achieve the goals that I plan to achieve. I'll talk of the simulation and test alongside with the results that I found out. And then I'll give a discussion and later on talk of the conclusion of my thesis work. So, bots, just like other vehicles, they are complex systems which contain a lot of subsystems in which these subsystems have been controlled with the thing called electronic control unit, which are small computers, and these ECUs, they basically generate different data that could be overused if they are basically properly used if they are used at the right time. So, for example, like an engine by Volvo Penta, it's a complex system that produces different data, for example, like engine health and warnings. So all of these data, if you get an access to them, they could be overused to either the owner of the bot or the repair person. So a bit about the data, they can be used to decide how soon or later the maintenance routine has to be done. They can also be used to tell how the bot is performing. They can also be used as alerts when there is a problem in the bot, or they can also be used as source of logs for different system-wide events. But then the thing is, with this data, the way we present them to the owner or the repair person is that the bots right now, they have really primitive displays, so they are not interactive and they cannot be easily accessible. And much worse, to basically display a new logic, you have to reprogram the whole ECU of that display. So Diadrom, the company where I was doing my thesis at, proposed a solution that would allow a Wi-Fi module to be attached to one of the ECU, to be specific, the one which is called Dynamic Service Module, which basically contains all of this information. And so with this implementation, these data can be streamed across to either a mobile device or a mobile phone, and users will be able to basically preview this data using their standard web browsers. But then, as you can pretty much see, displaying data on the standard web browsers, basically you will need to transfer this data across the Wi-Fi network using the HTTP protocol. And as you can already guess, these information, they are very sensitive, and HTTP is not very secure. So one way of approaching this security problem is basically by securing this HTTP content, in which HTTPS is where it comes in handy. And one of the protocol which is basically widely used for securing this HTTP content is TLS, which is basically the main focus of my thesis work. So a little bit about TLS protocol. It is the what protects your passwords and other sensitive information when you're browsing the web. For example, when you go to internet banking websites, various payment as well. And what this protocol does is that it basically encrypts your HTTP traffic as it is being moved across two different nodes. In this case, from one ECU to the mobile device. So this Tls protocol, in short, it basically has two parts, which is PKI, public key infrastructure, which is responsible for negotiating different encryption schemes and authentication procedures. And the second part, which is where the symmetric encryption happens, after agreeing on these keys and different session IDs. As you can see from this diagram, this is the TLS stack, which has the handshake protocol, and then this record protocol, which basically contains the encrypted data, which is to be transferred across two different parts. Again, as you can probably guess, these ECUs, they are pretty much limited in terms of capacity. For example, the MX4 computer that I was working on for this thesis work, it had like 500 megahertz of processor speed and 256 of DDR RAM. And if I remember correctly, it had like 500 MBs of hard disk. So they're pretty limited. And having all of this load of work to delegate it into this ECU to perform, it becomes increasingly important to understand the performance implication of this TLS before you even implement it into this device. So this was basically my main goal of this thesis work, to research and analyze the performance implication of TLS when it is implemented into vehicular embedded computers. And also, as a sub-goal, to follow some scientific methodologies so that it can help me to basically build a stronger understanding of the materials that I learned in class, like cryptography, network security, and computer security. So for this thesis work, I used an empirical research approach. And the only reason is because it kind of allows me to set a set of hypotheses and research questions. And then as I test these questions, it kind of gives me a deeper understanding of the whole research, the whole research subject. And at the end of the day, I reach my intended goals. So I started with information gathering, in which I remember we had a couple of workshops where I had to talk to the employees of the company, and they told me about the actual the industrial implementations that they are using, different protocols, how this work. And then I had to set some hypothesis formulation, in which I had some questions, research questions and hypotheses that I wanted to actually test. And the third step was basically preparing the test environment, whereby I developed a prototype as a proof of concept, and then I had to also implement this prototype in both cases where it uses TLS and where TLS is not implemented. And then I did the testing, and with the data I collected, I did the analysis of these data, and then I drew some conclusions based on them. So I'll walk you through very quickly the thesis, hypotheses and research questions that I set upon. The first one was algorithm requiring long keys degrade the performance. Much more secure implementation of Tls protocol causes the system to cost more. And then security and usability of the system proposed is affected by the performance of the vehicle embedded computer. The research questions were like, I wanted to know how long does the Tls protocol operation take to make a round trip? How does the performance of TLS affect usability of the system to the end users? And how can TLS protocol stack be simplified so that it can impact less on the performance and still providing some useful functionalities? So again, as you might have guessed, this system is not it's not used out there, so I didn't have some realistic information or data that I could use. So what I decided to do was basically create a simulation of actual usage patterns, and then with the Java program that I wrote, I did some tests based on these actual usage patterns of this system, so that I can look at them and basically analyze how does the TLS imply when it comes to performance of these computers. Yeah, so for the testing, I basically divided these tests into 3 categories. And these categories, they're basically very much in sequential order, because the results I got from the first test, it kind of directed me towards digging deeper into it and understanding whatever was not clear with the first test. So I had to go to the second test and then the third test. So I'm going to tell you a little bit more about these tests, the user test, HTTP connection test, and TLS operation test, and how these kind of helped me to answer the research questions and hypotheses that I had. So user testing, this was basically targeted towards trying to look at the normal user patterns of the user, how the user would want to use the system, and then based on it, try to see if there is any difference between TLS implementation and no implementation. For example, if in the prototype that I built, user wanted to, if for example user wanted to view information about the vehicle which were being basically streamed across the device, user will have to go to the login page first and then get the PIN from the display page, and then after entering the PIN, user will be directed towards the actual dashboard. So all of this, I took it as if it's basically one usage session, and I measured the time before the first request was made to the last request, and then based on this time, I did the same for both HTTP and HTTPS with TLS, and then tried to compare. And the results from it, they kind of told me first, HTTPS was taking a little bit longer, and to be specific, about 7% longer time. And another surprising fact was with this one, where the very first page to be loaded, they kind of showed they took so much longer time as compared to the other pages. And all of these, when I was testing this environment, I tried to make sure that if there were some libraries, they basically had the same content which has been loaded. So in a normal scenario, this should have been flattened out. But then this behavior, it kind of taught me and made this assumption that maybe the first part, it could be the time when there was TLS handshake and TCP handshake as well. So the same sessions were being used across the other ones. That's why they took less time. The second test, basically this HTTP connection test, involved a specific web page which I set up, and this web page was basically replying to me with the contents of the same size as the one which I have specified. So for example, here with this request here, I have specified the size that I need 230 bytes. And when the request was sent and when the response came, it was basically 230 bytes of random string. And why did I do this? It was basically I wanted to try to compare how does the payloads affect the whole process, and how, because with the HTTPS, these payloads are going to be encrypted, and there should be some useful information that I can gain from that. So what I basically did was to set up this web page, and then for a specific payload size, let's say 10 bytes, I make a request, and then as the request is being sent, I was measuring these parameters, which is the time it took to do the name resolution, time it took to do the redirection, time it took to do the TCP handshake, the TCP connection, this app connect, which was basically TLS handshake, and all of these other, like pre-transfer and the actual transfer time that all of these contents took. And this test, I basically, with that payload size, I specified, after I specified it, I did it the same. It repeated itself for like 1,000 times so that I remove all the noisy data and get the actual values. And then I move again to the next payload size, like 20 and so on. So with this test, at the end of the day, I got some really interesting data. It was so many of them, but I'll try to summarize them here. It showed that the total time basically for the HTTPS, it was basically a little bit longer, even though the data were kind of noisy, but then you can basically see the pattern. This is the unsafe values, these are the safe values with TLS. So basically you can see that TLS takes a little bit longer time, which is of course expected from the first test, which we saw TLS takes longer. What's surprising is that the other graph that I got showed that this T-App Connect was basically also taking longer, and for the unsafe one, it was basically registering 0, which means TLS handshake wasn't happening for the other one, and basically this could be the biggest reason for the delay that we saw when we are trying to compare the two. So understanding this, and another interesting factor I got, it kind of made me to go dive deeper into now checking the actual TLS, different ciphers and algorithms, how long do they take, so that I can maybe make some conclusions based on them. And so it came the third test, which was the TLS operation, in which I was basically looking at each of the algorithms in cipher, how much time it took, and this is the sample data which was basically coming from it. And the good thing is that OpenSSL had a special command that when you, for example, write OpenSSL speed and then you give the cipher name or algorithm, it will basically simulate that, do the actual testing for you, and then give you the results based on that. So I used this one to test for all of the supported TLS ciphers and encryption schemes, and the results, they were basically categorized into these three. So I'll summarize them with you. So I came to realize that as the key size becomes bigger, basically it takes longer for an algorithm to finish. So for example, like here, this MD5, with the increasing number of these key sizes, you can see that at the beginning it took less number of operations, but at the end it took so many more operations per second. Also, I came to realize that the payload size is also one of the factors which can make an algorithm to take so much longer. For example, here I was using elliptic curve Diffie-Hellman. The only thing I was basically changing was the number of payload size, starting with 160 bit, and to this one, you can basically see that the operations per time, this one took more operation because it was basically much faster as compared to this one. Or you can easily see it here. Like it took almost 130 milliseconds to finish, while the first one was only like 2 milliseconds. So the third one was basically some algorithms perform better than others. For example, like here you can see RSA and DSA. These are two different algorithms which have been used with TLS. In some cases, with the same payload size, RSA performs better and DSA performs worse. In some cases, DSA, for example, in this doing the signing, DSA was much better than RSA. So after doing all of these three tests, I came to realize that most of my hypotheses and research questions were answered. For example, the question about algorithm with long keys, they basically degrade the performance, which is basically true. Based on the data that I collected from the TLS operation, I came to realize that the longer the key is, then the longer the operation will take. Also, the second hypothesis about much more secure implementation causes the system to cost more. This one was also true because when you have much more security, which means you have really long keys, it basically kind of affects the security of the of your system, because it takes longer for these operations to complete. And yeah, and the other one, it was still unknown because it was kind of out of the scope. Security and usability of the system is affected by the performance of the vehicle. So this one was still unknown because my main focus was trying to compare the two and not the two against the performance of the vehicle. Some of the research questions, for example, I wanted to know how long does the TLS operation takes to make a round trip. Now you can even see that these questions were kind of dumb because from the results that we got, we came to realize that there are some factors which affect the performance of TLS, and not just TLS will perform this way. And these factors are like algorithm which has been used, the key size and payload size, just like how we found from the TLS operation test. How does the performance of TLS affect usability? We also saw that some results showed that the usability was basically affected because there are some cases where the system with TLS responded so late, almost more than 300 milliseconds. So that kind of makes it notable to the users. So usability becomes really bad. And also the last one is how can we TLS protocol be simplified so that it impacts less on performance. And for this one as well, I just came to realize that TLS as a protocol is just okay the way it is. It really comes down to the three factors that I found earlier. These factors are like the payload size, the key size to be used, and the payload and the algorithm which has been used. I have seen there are some cases where an operation takes 2 milliseconds, and there are some cases where operation takes 130 milliseconds. So it really comes down to that, and not just the fact about TLS protocol. So some recommendation about some future works is that it could be interesting to look at the performance of the TLS from the really lower level. Maybe you look at the actual algorithm, maybe MD5, and how each of its components could be, how does it perform. Also trying to compare the security and power, because I understand that these issues, they really need to be power efficient. So if at all security has some effect on power usage and things like that, it could also be interesting. And then do some complementary on the open source software that I did for the actual testing, which could also add more support to other, even other operating systems and other devices as well. So some takeaways from this research is that HTTP basically performs better than HTTPS. The factors that are influencing the TLS are basically the key size, payload size, and algorithms. And also, TLS as a protocol is just okay the way it is. It really depends with the algorithms and ciphers that have been used. That can be a direct cause of performance problems. Yeah.
All right. So, thanks. Now we'll begin with the opposition part. Go ahead, and then we open the floor for questions from the audience.
So, what is your study? We test the implementation of the TLS as a protocol security.
Yeah.
But the final result, we found the HTTP performance better than the HTTPS.
Yeah.
And also we found that, through implementing the three tests, that affect the key size, the payload size, and the algorithm performance as well. From your point of view, do you support the implementation of TLS since it's a security protocol?
Yeah, so I will say, just like the way I concluded the last point here, TLS is pretty okay the way it is. It really depends on what kind of algorithms you use. So I would say, looking at the good that comes out of TLS, I think it's a very good protocol to be used, and it provides some useful features like encryption, providing all the security techniques to prevent some security threats. So I pretty support it, and the question becomes, it really depends on what algorithms have been used and how do you configure your TLS.
Okay, and also during your study you mentioned the reliability and the performance as a quality What's the other quality that you get affected by the implementing of HTTPS or TLS?
Well, I mean, using maybe, I think it could have an impact on power as well. Yeah, but
Power consumption.
yeah, power consumption, because I presume these processors, as they process, they could use so much power, and so I think this is kind of another thing that could be affected by these TLS operations.
Okay. Thank you very much.
All right. So, any more questions?
Can you give us some guidance here on what the optimum key size, payload size, and algorithm would be for the MX4 you choose? Where are we? Where does it start affecting the usability? Where do you hit 300 milliseconds?
Yeah. So so in the report I had some much more description on this test, and as if you look at them, you can start seeing the kind of algorithms that they basically take longer, the key size, for example. This one is the key size.
Complementing is every one of these algorithms here accessible from a standard web browser such as Chrome.
Yeah.
Pretty funky.
Yeah, so using the chat like this one, you can basically start looking at what could be the most probable key size, maybe. I think it's the first one. Yeah, these key sizes, and then you can look at each, and then basically make some recommendation based on how much time you want your system to perform. Because I think these details, they are pretty specific on how you want the system to perform. You may be fine with 1 second delay, maybe 1 second is too long for some cases. So it really comes down to the chat like this one. And the good thing about this Thesis work is that there is an open source software which is available. So you can basically use that software to test for your own device and see where it is. Yeah.
Put yourself.
Yeah. Yes.
I don't know if you had any thoughts about this, but since TLS is, if I understand it correctly, end-to-end secure tunnel, wouldn't that eliminate the need for Wi-Fi encryption and save power consumption and performance from that perspective?
I think, but then, because in this case, for example, if from my understanding is that if you have a Wi-Fi and you put maybe a passphrase, whoever is within the network has the ability to also decrypt or whatever the communication it is. We wouldn't know where an attacker would be. It could be from within the network or from outside. So I think this will be the best way to basically secure this communication.
Good point.
I have one question. So when I see your conclusions and your take homes, I mean, they look obvious, right? I'm a security expert, so it looks obvious. Security takes some cost. But related with the question that he did, it's like, if you want to wonder where, now that you have all the numbers, because now you have all the numbers, and I said, where I draw the line. I think we're discussing about the key size, the payload size, the algorithm, but we're not asking about what is the type of security that we want with a boat, for example. Do I want military encryption with a boat just to send me how fast I'm going or not? Right? So what is your impression about this? What is the requirements that they are thinking of, because if you know that, then you can draw the line and say, okay, we don't need like, 4,000 bits key.
Yeah.
1,000 is okay. Because the communication is only about, my speed, the level of oil or whatever.
Yeah.
I might not care about confidentiality at all. I might care about integrity, that the
Yeah.
device doesn't inject commands into the engine. But I'm fine with the engine reporting things to the public and people seeing. I'm fine with that. So what is your impression? I mean, you've been working in this company, so
Yeah. So
what do they want?
I think I had a discussion on this one with Henrik, and I asked him about I think after we had a discussion, you told me maybe I should ask the company what are the sort of time delay that they can basically tolerate, and from
And the
what
security that they want, because it would be like
yeah,
a trade-off.
yeah. But then from the way I spoke with Henrik, I think it really comes down to it really comes down to how the specific system wants. How the end users want the system to perform. But from the general look of it, I think he was pretty okay with with the value which I speculated would affect. I remember I talked about 300 milliseconds as the limit for the user-to-computer interaction to be noticeable to the end user.
Right.
But then 300 milliseconds, it may not be realistic in some cases as well. So, yeah.
In the high volume cases,
Yeah.
300 milliseconds would be the boundary
Yeah.
where it's too
Yeah.
slow. However, if that happens on the startup, it doesn't matter at all, because then once. But if the ongoing interaction is affected like that, so that's our first sort of requirement. Problem with our industry is that we can always come up with something. It might not seem sensitive now, but we gotta have a path of making it more secure, because there's always a salesman somewhere selling something to a military guy somewhere who wants super secure stuff. So you gotta be prepared.
Right.
But on the other hand, if it's a military application, then cost is not a problem.
Yeah.
If it's a private, even though the guy is rich, Henry Ford is still the ruler of the automotive industry cost and pressure. So then 50 cents of processor is looked at. In the military industry, $500 is a no-brainer. So it's totally different application. But what I can say is one of the things that you want to do is that you want to change as Tesla are doing right now. Everyone's talking about it. Everyone else will be doing it too. But Tesla is very loved because that Musk guy. Anyhow, they do remote updates, and that's kind of important because you're updating a very safety critical system with a whole family and small children that is running 100 miles per hour. It's got to be done in the right way.
Yes.
So when you do any right operation will be subjected to a lot of security thing. However, these right things are often unsupervised. It's not a high interaction procedure.